Hi, my name is Dear Tiagi, and in this video, I'll be going over oscillations for Unit 7 of AP Physics 1. So to start, what is an oscillation? An oscillation is defined as an object that goes through periodic motion around an equilibrium point. An example would be, we'll go through examples later on. But first, let's define types of oscillations. So there are multiple types of oscillations, but for the AP Physics 1 exam, the only one you need to know is simple harmonic motion. And there's other types of oscillations. Obviously, there's damped oscillations, forced oscillations, etc. But for the AP Physics 1 exam, the only one you need to know is simple harmonic motion. And so in simple harmonic motion, what happens is there's a restoring force that is proportional to distance from equilibrium. Okay, so during simple harmonic motion, there is no energy lost, and the restoring force is always proportional to the distance from equilibrium. Okay, so now let's look at some types of simple harmonic motion. So the first type is if there's a spring. So an example could be if we had a spring, like so, connected to a mass, and it was oscillating back and forth about, let's say the equilibrium was here. So in this case, there's one important formula you need to memorize for this kind of case. Whenever we have a spring and it's going through simple harmonic motion, then the formula for the period is equal to 2 pi root mk. Again, what is the period? The period is the time it takes to complete one oscillation. Okay, so one oscillation could be from the equilibrium out, back, and back to equilibrium. That's one full oscillation because it starts at one point and it returns back to that one point. So it's one oscillation. So the period tells us the time it takes to complete one full oscillation. And so what this formula shows us is that the mass, the period for a simple harmonic motion system with a spring is equal to the mass divided by k and square root of that times 2 pi. So the only things that matter is the mass and k, which is the spring constant of the spring. Another thing to know is that you guys should know this, that angular frequency is equal to 2 pi over t. And again, angular frequency refers to how much time it takes to complete a angle in a circle. Because again, look, if we had a circle like so, then 2 pi would be around the circle, one full time around the circle, and t, the period, would be the amount of time it takes to go one full time around the circle. So omega, or angular frequency, tells us how much time it takes us to go through one tiny little unit. And so from this formula, we can see that period is equal to omega over 2 pi, and then omega over 2 pi from this formula, 2 pi over omega, so 2 pi over omega, and therefore, since 2 pi is there, omega has to equal to root k over m, using these two formulas. And finally, there is one more system you need to memorize the formula for, and this is for a pendulum. So if we have a pendulum, and again, for pendulums, this only works for small angles, because for the derivation of this formula, what we use a small angle approximation to derive it, but all of the questions you'll get on the physics exam will be small angles unless they tell you it's not a small angle. But anyways, small angle, so in a small angle pendulum like so, that's oscillating back and forth, my marker is dead, the period is equal to 2 pi root Lg, and then because of that, omega, angular frequency, is equal to root g over L. And so for a pendulum, the only thing that matters is the length of the string, so L is here, length of the string, divided by gravity. So mass doesn't matter in this case. Mass doesn't matter, gravity doesn't matter, etc. So it's different cases for each. One more thing, frequency is equal to 1 over the period. And what frequency tells us the number of oscillations per, I really butchered that spelling, per unit time, okay? So if having a frequency of, say, like 50 hertz would be 50 oscillations per 1 second. Hertz is equal to 1 over a second. And one more thing, graphing simple harmonic motion. So graphing is less common. You really need to know those two formulas, though, period. Those are really important. Graphing is a little less important, but I'll go over it. So let's say we have a spring connected to a mass, and let's say it starts from here, and this is the equilibrium point, so it's going to go this way, then it'll go back, etc. So now let's try to graph its motion. Let's call this x is time, let's call this distance, so x, and let's call this equilibrium. So initially, it's negative amplitude away from equilibrium, so here. We'll draw the x position first, so its x position is here, away from equilibrium. Then here, we'll call it, that's at equilibrium here. Then it goes away from equilibrium, back to equilibrium, and back to starting point. So this is one oscillation, and this would describe its position, because again, it's going to go really fast to equilibrium, then as it approaches the end, it's going to slow down, which is what our graph shows, and then it's going to speed up, slow down, speed up. So this is why it's like a wave like this, and this is our position. Acceleration. So our acceleration here is going to be positive, because we're going to be accelerating in this direction, because our k is here, and we're negative equilibrium, so it's going to be positive. So acceleration is going to be here. Then when we get to equilibrium, there's going to be no acceleration, because at equilibrium, we know that the force of the spring is equal to, is equal to 0, because it's at equilibrium. Delta x, k delta x, right, is force of the spring. Delta x is equal to 0. So equilibrium, we're at 0. Then when we get to this side, our acceleration is negative, because our velocity is increasing to the left. So we go here. Finally, we go back to equilibrium, so our acceleration is 0. And we get a graph that's basically just a mirror image of the x graph. And finally, velocity. So here, our velocity is 0 because we're at stationary. We just reached the end and we're stationary. So our velocity is 0. But then what happens is we're accelerating positively, so our velocity increases to here. And so when we're at equilibrium, our velocity is the fastest because our acceleration is 0 and we've been accelerating for this entire time here. Then what happens is our acceleration becomes negative, right? Acceleration is negative, so we're losing velocity until we go to 0 at the end. Because when we're at this end here, our velocity is 0 because we're just stationary and waiting to be accelerated the other way. And then same patterns, then when we go back to equilibrium, our velocity is going to be fastest. And then when we get back to here, the origin, our velocity is 0. And that's our velocity graph. So if we want to quantify these graphs using functions, we can call x of t equal to a cosine omega t. We can call velocity of t the derivative of x of t, which is negative a o omega sine omega t. And finally, acceleration of t is the next derivative, so it'd be negative a omega squared cosine omega t. And those are the formulas for the graphs of our equations. And so you don't really need to know these equations all too much. Just know the graphs, how to graph, and these equations are kind of just describing the graphs. You don't need to know those. Okay, let's try some practice problems now. So let's say we were given the problem that we had a pendulum, a simple harmonic pendulum, like so. The length of the string is 1.53 meters, and it's oscillating, right, simple harmonically. And we know that its frequency is 24 oscillations per minute. So that's the frequency. And we want to find what gravity is equal to on this planet where this thing's oscillating. Based on this information, 1.53 meter long string, and frequency is 24 oscillations per minute. Okay, so we know the formula for a oscillating pendulum by simple harmonic motion is t equals 2 pi root Lg. Okay, and we want to find g. So I'll move the 2 pi to the other side, and I'll square it, and I'll get t squared over 4 pi squared is equal to L over g. Then I multiply g G, and I move t squared 4 pi squared to the other side, and I get L times 4 pi squared over t squared is equal to G. Okay, so what I know what L is, right? So I have L, 4 pi squared, just constant, I know that, but I don't have T. What I do have is frequency. And so if I can take the frequency and make it into T, I can be able to solve for G. So first things first, we have to change the units on frequency if we want to convert it to T, because gravity is in meters per second squared. So we want all our units to be in meters or seconds. So this is already in meters. This has to be in seconds, so let's convert it. So this is 24 oscillations. Oscillation is dimensionless, so we don't have to write it down, per minute. And so we can do the conversion. 1 minute is 60 seconds, and we get our frequency in terms of seconds, which is 0.4 seconds to -1, which is hertz. Okay, and we know that frequency is equal to 1 over t, and so therefore t is equal to 1 over frequency. And so from this, we know our t has to be equal to, I believe, 2.5, right? 2.5 seconds, so it takes 2.5 seconds to complete one oscillation. And now if we plug it into our formula, what we get is that G is equal to 9.65 meters per second squared. So close to Earth's gravity, but not exactly, so they might be higher up or on a different planet maybe. Okay, so just to reiterate the process here, we identified our equation, then we used the quantities it gave us to, we converted them to units that we needed, and then we plugged it in to find our answer. So again, most simple harmonic motions problems are usually pretty simple. They usually rely on like this equation or the one for the spring, and all we have to do is plug it in and find the answer. Okay, we'll do one more. This one might be a little bit harder, but it's again the same principle. So let's say we have a trampoline, and there's a person up here who's 0.6 meters away from the trampoline. This person weighs 70 kilograms, and this person's going to bounce on the trampoline. And so when this person bounces on the trampoline, she bends it, or fracts it, I believe, 0.4 meters, like so. Okay? And the motion of the trampoline, so the motion of the bouncing, is simple harmonically motion. It's a simple harmonic motion trampoline as well. And let's say we want to find the period. Okay? So even though this isn't like a clear spring problem, we know that trampolines have springs, and we know it's simple harmonic motion, and therefore, because it involves a spring and it's simple harmonic motion, we can use the fact that period is equal to 2 pi root mk for a spring system that is in simple harmonic motion, which this is because trampolines work using springs. So with this formula, we know the mass, right, 70 kilograms, and we don't know the k, so we want to find the k. And to find the k, okay, so we know the height, and we know that it diffracts 0.4 meters. So what we can use is energy. So we can say that here we have an energy, UG1, and here we have a energy, all spring, US1. Okay, so call this here UG0. And so we can say that UG1 is equal to US1, so gravitational energy here is equal to spring energy here. Gravitational energy is equal to mgh, which is equal to kx squared over 2. And solving for k, we get that 2 mgh over x squared is equal to k. Okay, so 2 mgh, our h is going to be from 0.6 plus 0.4, because we're going from, this is ug equals 0, so 0.4 plus 0.6, we're changing height of 1 meter, so times 1, over x squared. X is a displacement. We're displacing 0.4 meters from equilibrium, so 0.4 squared. And if we do this, we should get that the answer is 8,750 newtons per meter. And now we can finally plug it in, and we'll get our period is equal to 0.57 seconds. And that's the period for the trampoline oscillation. So again, a fairly simple problem here. All we have to do is identify the equation, solve for whatever values using the other information, and then we're able to find our period or our answer. And that's how you do Unit 7 oscillations. Thank you guys all for watching, and I'll see you guys all next time. Bye.